Hello, welcome to the presentation. This is my Project 1 GUI presentation. My name is Elijah Johnson, and let's get started. Today we're going to talk about key features, example transfer functions using my app, and challenges I faced while building this GUI. Some of the key features that we're going to talk about and were outlined in the rubric that we were provided, where we're going to have some bode plots that plot the magnitude and the phase. We're going to have our step response plot that we've done plenty of times. We actually have our root locus plot that will give us both our zeros and poles. We also have our system information. This is going to give us all our gain and phase margins and all the other things when you type in system info in MATLAB for the transfer function, and it gives you all those beautiful pieces of information. And lastly, but most importantly, your inputs. You have your numerator, your denominator, and your frequency range. These are all things the user will decide to put in to whatever their desire. Here is kind of the example with one I put in. We're not analyzing it just yet, but it's just to see what it kind of looks like. We can see the root locuses, we can see the step response, and how they kind of all fill in beautifully. But the beautiful part about this app is it's real-time analysis. You're putting in whatever transfer function you desire, and you get to see the roots, the poles, the step responses, all these beautiful things that sometimes not everyone can just look at a step or transfer function and just visualize it like this. And so it's a beautiful tool when understanding stability and other things that are involved with your transfer functions. Here's example number 1. So in example number 1, I chose this s squared plus 3s plus 4 over s squared plus 5s plus 6. Now simply enough, we just grab the coefficients and include them right here. So we have our 1, our 3, and a 4 coming from this numerator. And we have a 1, a 5, and a 6 coming from this denominator. And then I chose the frequency range of 0.1 to 1000.7, just so it shows how massive you can get the frequency range. We can look at this after we've pushed analysis. We can see now what happens, what this transfer function creates, and all the beautiful aspects that involve it. So I tend to like to look at root locus first, because root locus gives you what the poles and the zeros are, and you can see these are going to be zeros because this is where the numerator actually turns to 0 based on if we factored this out. And you can see that it's on the imaginary scale because when you factor it out, you're not going to get even numbers like the roots are. Well, there are -3 and -2. They're just whole numbers. They're perfectly real. And this is a beautiful example for stability because when you see that there are imaginary and real roots in the negative, on the real axis, on the negative side, it confirms a stability that this function has, or system has. And you can additionally see in the step response right here that it does oscillate a little bit beyond stability point, but then it comes back and levels out. And that's just a good sign of stability in that instance. And beautiful from this one, we can see that it actually had a 50% overshot and a 2.07 second time for it to settle, or settling time. And all these can, you just look at the system info and you can look at these and they should correlate. They should be exactly the same. And then one other thing that I like to look at is my gain and phase margin. Now, MATLAB had a little interesting math part with this, making this phase margin -180. Usually that's a sign of instability if it's in the negatives. But in this case, it's actually stable, and 180 is like the most it goes to before it turns over. So that was kind of like, because it's supposed to be infinite. Infinite meaning that you could add any form of phase shift or gain shift or decibels to make this alter it in some way, and saying that it's infinite means you can add as much as you can and it's not going to change, meaning it's stable at all points. That's kind of what this gain and phase margin is supposed to indicate for us, and we can see the impacts of the poles and the zeros right here on this bode magnitude right about here, and similarly over here at the bode phase, where these poles reach is what really affects these bode and phase magnitudes. Let's go on to the next problem. Now I chose this one specifically to find an unstable system. And this one I kept the numerator 1 and then s squared plus 1s minus 2. 1, 1, -2. Same thing as before. I did, however, shrink the frequency range to be 0.5 to 100. Only you can see that it's logarithmic as previously, and it just stops at 100. Beautiful enough. Now this one is just simple, pure, real roots. There's going to be one at -2 and one at 1. Now, when you identify this immediately, there should be a red flag. Oh, this is going to be unstable. Because we have a rule that says if there's any real root or imaginary root that's beyond or on the positive side, it's most likely going to lead to an unstable system. And then you look over here at the step response and you see, all right, my judgment was accurate, because you see how this starts up here and then it reaches here and it just climbs forever. That's going to show you that it's unstable and there's no stability that it will ever achieve. And oftentimes you can be backed up by looking over here and it says not applicable, meaning that there is no settling time, there was no overshoot, none of that happened because it's unstable. Now it does, however, mention that a gain margin of 6.02 decibels could be added to the system to help to possibly stabilize it, but we really just look at this to emphasize that it's an unstable system. And then we can see right here with the Bode and phase plot, most of the time, like I said before, you look at your poles and those are what influence your Bode and phase magnitudes and how they respond. Now, here's where I know you love to see what happened, and when it came to this project, there were definitely some challenges that I faced. One being, I did use the GUI app design assistant tool on MATLAB, and that I had to basically watch a bunch of videos to help emphasize like what it is, how it works, how do I modify the code, how do I learn these tools to help assist with it, because I believe it really helped me place everything properly on the app to make it look very pleasurable. But to my disadvantage, there was some code parts that I had to learn pretty significantly, which leads into my second part, which was calling features in the app, and mostly revolved around the properties tab, because I implemented these text field boxes that you could change, but I added a numeric one. And the challenge I had to overcome there was the numeric one was causing issues regarding how the user would input. They'd have to, input numbers, right? Fair enough. That's what we've been doing. But the spaces would throw off the computer program. So I had to adjust that to a actual just text field receiver, so it receives string text rather than numeric text, and then I would translate that string text to numbers, allowing for the spaces to be analyzed properly, and then it fits into a nice array in the end. But I had to use like classmates code to see how they did it, and I saw that theirs wasn't a numeric editable field, it was just a regular text editable field, and that was the biggest thing I take away right there. Lastly, one thing that I was struggling with was the Bode graphs, as I imagine everyone was, and there are some really capable individuals. The Bode graphs wasn't functioning to what I desired, because I was trying to use the one we had in class, and the one we had in class was a very specific transfer function, so I was trying to understand how can I implement this on the bigger scale, like for any transfer function that someone adds, because the whole point of the Bode plot is that they multiply the j omega into the polynomial of both the numerator and denominator, substituting for the s, but I didn't know how to do that across a multitude of different transfer functions, because they could only put in like a 1, say, in the numerator, and then there is no s squared or s, but depending on how the code was read, it would have to understand that and analyze that. And so I asked ChatGPT to help me with what is some brainstorming ideas, and actually found this function, I think it's called polysave, that we were able to use, and it basically goes through the numerator and denominator polynomial and substitute that value in for that spot. So it was basically, I had my loop iteration going on, and then I just needed to figure out how I could substitute internally that w into, or that j omega into the s spot, and I was able to figure that out with through the use of ChatGPT and a little bit of my own modifications, as well as heavily relying on what we did in class to analyze and see how we would generate a Bode iteration. And that was really it for most of my main struggles and how I overcame them.